Good morning to all. This is Dr. S. Harnath Babu, Assistant Professor of Physics, Annamacharya Institute of Technology and Sciences, Rajampet. Today we discuss the characterization of the materials, XRD and SEM. First we discuss the XRD analysis. X-ray diffraction is one of the most important non-destructive tools to analyze all kinds of matter, ranging from fluids to powders and crystals, where Bragg's law is 2d sin theta is equal to n lambda. If any incident X-ray satisfying the Bragg's law with crystal planes, then only that X-ray diffracting occurs. In Bragg's law, 2d sin theta is equal to n lambda. N is an integer. Lambda is the characteristic wavelength of X-rays impinging on the crystal sample. D is the interplanar spacing between rows of atoms or crystal planes. And theta is the angle of X-ray beam with respect to these crystal planes. Or it is also called Bragg's angle or angle of diffraction. Here we can discuss the periodic arrangement of atoms along x direction, y direction, z direction. So here the circles are atoms arranged periodically in x direction, y direction in the given crystal. Here the blue color lines, two blue color lines are indicating two crystal planes. The interplanar distance is given by small d. Next, red color lines representing the incident X-rays. So where the characteristic X-rays having particular wavelength lambda are incident on the crystal plane with angle theta. The incident X-ray makes angle theta with the crystal plane. If the incident X-rays satisfying the Bragg's law 2d sin theta is equal to n lambda, then only these X-rays are diffracting from the crystal planes. So these X-rays are diffracting or scattered or reflected in other direction with angle theta. So these X-rays are detected by the detector and we can analyze the grain size of the material and structure of the material. X-ray diffractometer. X-ray diffractometers consists of three basic elements: an X-ray tube, a sample holder, an X-ray detector. Characteristics of X-ray spectra are produced. These X-ray spectra consists of several components, the most common being K alpha and K beta. These specific wavelengths are characteristic of the target material: copper, iron, molybdenum, chromium. So here it is the X-ray diffractometer. Here three devices are important devices, that are X-ray source, sample stage. Next, third one is X-ray detector. In X-ray source, already we know that production of X-rays when oscillating high intensity electron beam incident on the target material like copper, molybdenum, tungsten, etc. Then the X-rays are produced. So the energetic electron beam or electrons incident on the inner electrons of the atoms of target material, then the electrons are emerging out, inner orbit electrons are emerging out, then the upper orbit electrons are jumping into the lower orbit, then energy is emitted in the form of characteristic X-rays. These X-rays are emitted from the X-ray source. These X-rays incident on the sample material with making angle theta. Then if the incident X-ray satisfying the Bragg's law, these X-rays are diffracting from the sample. These diffracted X-rays are detected by the X-ray detector. So the angle of diffraction is also equal to theta, where the angle between incident X-ray direction and diffracted X-rays is taken as 2 theta, where by using this value 2 theta and interplanar spacing, then we can identify the crystal structure. Here the typical X-ray diffraction pattern of the cement. So for different materials the X-ray diffraction pattern is different for copper, for iron, for molybdenum, for different metal oxides, for different alloys. The X-ray diffraction pattern is different. So here the theta value, angle of diffraction is taken along x direction, 2 theta value is taken along x direction, and intensity is taken along y direction. So these X-rays incident on the material, within the material or crystal sample, there are number of crystal planes are oriented in number of directions. In different orientations are there, vertical direction, horizontal direction, vertical direction. Similarly, in different direction orientation of crystal planes are available in the material. So these incident X-rays, incident on the crystal plane and diffracted, and these diffracted X-rays are detected by the detector. So here, if the number of peaks are given, so one peak has more intensity, one peak has less intensity, etc. So these different peaks are diffracting with different angle of diffractions from different orientation of crystal planes. So there are the orientation of crystal planes are determined by using the Miller indices H, K, L values. So for example, there are number of Miller indices or crystal orientations are there in the given material, like 110 orientation, 100 orientation, 111 orientation, like that. Number of orientations are available. So from each orientation of crystal plane, the X-rays are diffracted. These diffracted X-rays producing the circle shape of image. The circle shape of image intensity is recorded in the diffractometer, and you can observe the data. So 2 theta value is taken from the x-axis, then the particular crystal plane has intensity is identified on y-axis. So by using the full width at half maximum value, then we are note down, and by using the interplanar distance and full width at half maximum value and the theta value, then we can find the grain size of the material. And by using this technique, we can identify the unit cell parameters also, A, B, C parameters. So here the different intensities of crystal planes are given. So this crystal plane, orientation of crystal plane giving maximum intensity. So this orientation is crystal plane is dominated crystal plane. Remaining are less intensity crystal planes. So XRD crystal applications. Characterization of crystalline materials. Second one, identification of fine-grained minerals such as clays and mixed layer clays that are difficult to determine optically. Third one, determination of unit cell dimensions. Fourth one, measurement of sample purity. Next we discuss the scanning electron microscope. Next one is scanning electron microscope, SEM. So already we know that two different type of characterizations for surface morphology of materials. First one is TEM, the transmission electron microscope, which detects electrons that pass through a very thin specimen. Second one is the scanning electron microscope, which uses the electrons that are reflected or knocked off the near surface region of the sample to create an image. Next, in scanning electron microscope, there are mainly three parts. First one is electron console. It has knobs, switches that are used for adjustment of filament current, accelerating voltage, focus, magnification, brightness, and contrast. Next, electron column. In electron column, there are different parts that are electron gun or electron source. Next, anode. Next, condenser lenses, apertures, scanning coils. Next, aperture, objective lens, etc. Next, third one is specimen chamber. In specimen chamber, there is sample stage, controls, and detectors are available. So first we discuss the electron gun. So in electron gun, there is one filament the current passing through the filament and filament is heated, the electrons are emitted by thermionic emission method. So these filament is kept in the Venelt cylinder. So this Venelt cylinder controls the number of electrons emerging from the electron gun. These electrons are primarily accelerated towards the anode. So this anode has positive charge. Then the electrons are converting into a fine beam of electron beam with high energy, and the electrons are passing through the condenser lens. When condenser lens is the device which has copper coils. When current passing through the copper coils, magnetic field is generated. The electron beam is sensitive to the magnetic field. So when electron beam is passing through the condenser lens, then the beam is converged and pass through the focal point, so that the electron beam is focused down to 1000 times with original size. So, condenser lenses are responsible for determining the intensity of the electron beam when it strikes with the specimen. So next, the apertures. So below the condenser lens, apertures are available. So these apertures are used to reduce and exclude extraneous electrons in the lens. Below the scanning coils, another aperture aperture is available. This aperture is used to determine the diameter of the electron beam or spot size of the electron beam. So that spot size determines the resolution and depth of the field. Next, the electron beam again passing through the objective lens, and again the electron beam is converging, and the electron beam incident on the sample. So here the scan coils are also available. These scan coils are used for rastering the electron beam on the sample. Then only the image is formed. So next one, the sample chamber. In sample chamber, sample is available. Next, controls and electron detectors are available. When electron beam incident on the sample, then the secondary electrons are emitted and backscattered electrons are emitted, and X-rays are also emitted. By using these, we can find the different images. Working of SEM. Backscattered electrons belong to the primary electron beam that are reflected back after elastic interactions between the beam and the sample. So when electron beam incident on the sample, then electron beam is scattered from the atoms on the surface. Then the scattered electron beam is called backscattered electron beam. Next, on other hand, the secondary electrons are also emitted. If electron beam, high energetic electron beam interacting with the atom, then the innermost orbit electrons are emitted by the inelastic collision. Then electrons are emitted. Inner orbit electrons are emitted. These electrons are called secondary electrons. So on the other hand, the secondary electrons originate from the atoms of sample. They are a result of inelastic interactions between the electron beam and the sample. Next, if inner orbit electrons are emitting from the atom, then immediately the upper orbit electrons are take transition to the inner orbit positions. Then the energy is emitted in the form of X-rays. These X-rays beam is used for analysis, the elemental analysis, where it is the backscattered electron image it is the secondary electron image. These are used for morphology study of the material.